In this video, I'm going to talk you through about calculating with friction, including some examples using the coefficient of friction for both static and dynamic friction. This is part of topic 2.2 of the IB Physics Syllabus, so it's part of the SL and HL components. Please take a moment to read the success criteria for this video. Okay, so let's start off talking about friction with how we could get some data from an experiment. So in this picture, I have an example of having a block here, and I'm going to pull it with the string, but I also have a force sensor right here that will then go to my Logger Pro. And if I pull on it, I can get a graph that looks similar to the one I have here on the right. Notice that on my y-axis will be force. And in this case, I have time on my x-axis, but I also could have been get a similar thing if I was pulling it with a certain force. So let's look what happens. You know that when something's not moving, if you pull on it a little bit, it doesn't move. I could probably pull on it with a little bit more effort. It still doesn't move. And that's what this line right here is saying. So every time I pull and it doesn't move, Newton's first law tells me that if the forces are balanced, they'll be traveling at a constant velocity. And in this case, my constant velocity is 0. So some people say an object at rest stays at rest. So I'm going to keep pulling on it, pulling on it, pulling on it. Notice my force is getting larger and larger. And as this happens and my force gets larger, I'm going to have an equally great force due to friction because my block isn't moving. But all of a sudden, once I get up here, I have something and it drops down. Now, this doesn't look perfectly straight, but it's a real life example here. It's kind of fairly flat though. So what happens then is I have a certain amount of friction happening as I pull on the block and it's not moving, and that will increase to a certain value. But then once it is moving, I seem to have a constant value of the force of friction. Well, let me give you a more simplified version, cleaned up version of this graph. So here we have the cleaned up version. On my y-axis, I have force of friction and absolute value signs, which just means I'm talking about a positive value. On my x-axis, I have the force applied that parallel to the surface, and we know that these two forces are going to be along here equal in magnitude, opposite in direction. When it starts to slip and slide, then we have this friction force here. And as I said, it's fairly constant, and we will consider it a constant force. So as it's not moving, we call it static friction. Once it is moving, we call it dynamic friction. Now, these are the two equations from the IB data booklet. Yep, I love my data booklet. But it's really important that we kind of look at them in detail. So big F standing for force, little f here standing for friction, is going to be less than or equal to a maximum value. That would be right here. Now, what is that maximum value? It's going to be the coefficient of friction times the reaction force. Now, I tend to call it the normal force, and in fact, in the previous versions of the syllabus for IB, it was considered the normal force, F with an N for normal. The reason I say that is because this is always going to be perpendicular to the surface. Now, coefficient of friction, you notice we have an S and we have a D. So static friction and dynamic friction. For the force due to static friction, it's going to be less than or equal to this maximum value. That was this one right here. And if it's starting to move, then this coefficient of dynamic friction multiplied by the normal force will give me this value here. Notice that the coefficient of dynamic friction is lower than the maximum value we get for static friction. And this is part of the reason why when you get something moving, it's harder to get it moving, but then once it is moving, it's easier to stay moving. Many people will talk about something called inertia, which is true, but this is talking about forces. So the actual force that's opposing you will be different. And one last thing about this coefficient, we can see here that we've got the force of friction equaling this coefficient times another force. That means that this coefficient is just to do with the ratios and it has no units. This value should be small, less than 1. I can't remember if that's a rule, so be careful with quoting me on that. But I can't think of an example off the top of my head which would ever give a value greater than 1. So let's work with this coefficient of friction and do an example. I always have to draw a little sketch with these diagrams. The coefficient of friction is between a 4 kilogram box, a 40 kilogram box. That's its mass. There's an arrow for its weight. And the horizontal floor is 0.2. What's the maximum horizontal force that could be applied without causing motion? Well, I'm going to look at our equation, force of friction. I'm going to put an equal sign because that will be the maximum value and the reaction force. Now in this case, because that box is not accelerating in any direction, all forces are balanced. And that means in this case, our reaction force is going to equal the force due to gravity. That means it will be equal to mass times gravity. When I put my values in, I will get a value of 78. I've rounded it to 2 significant figures because that's all I have in my coefficient of friction. So since I used force of friction equals the coefficient of static friction, R, that will give me the maximum value then of force of friction. If I give anything more than that, then what I'm going to get is I will have, it will be able to move, and then as soon as that happens, remember the force of friction will actually decrease. Okay, a rubber puck has a mass of 0.25 kilograms. It slides across an ice rink at a steady 3 meters per second. Again, the steady 3 meters per second tells us that it's going at a constant speed, and therefore all of the forces must be balanced. That means if it's moving forward, then if it's being pulled across, then there is a force being applied that will equal the force due to friction. In this case, the force is going to be constant because we have dynamic friction. It's moving. In this question, I've called it kinetic friction. Realize that that means the exact same thing as dynamic friction. So here's my equation, and we've got that the force of friction is 0.4. We have mu d is what we're looking for, and it's not accelerating vertically, so that means the reaction force equals the force due to gravity, which will be 0.25 times 9.81. And I'll pick up my calculator. I've got 0.4 over 0.25 times 9.81 to get 1.6. And again, I've rounded my answer to 2 sig figs because that's what I have in the data that was given to me. There are no units for the coefficient of friction. Okay, now we're going to get into something a little bit more tricky because it's not going to be on a flat surface. We have a crate on a hill, and we want to, we've got 25 degrees here. There's my crate. And we want to know how much friction will be needed to just stop it from sliding down. Well, let's put on some forces to begin with. We have the force due to gravity pulling straight down. We are going to have our reaction force perpendicular to the surface. I'm calling it Fn, or we could use the capital letter R. And then I would have the force due to friction parallel to the surface here. Now in this case, we've got vectors in all different directions. So what we're going to need to do is break some of these into their components. Now, if I broke this down into vertical and horizontal components, I would actually have to break the force due to friction here, as well as the normal force. But if I would actually then break it instead parallel to the surface and perpendicular to the surface, then all I actually have to do is break down this force due to gravity. So if I write its components like this. Now, one of the things that's important here is to realize that this angle right in here is 25 degrees. So let me just try and help walk you through that. If this is 25 degrees here with 90, then up here we need to have 90 minus 25. So this will be 65 right here. On the other side of that x, this would be 65, 95, 90, and then 25 up there. I leave it to you to do the geometry a little bit more if you don't see it right away. Now, let me take this force due to gravity and let's figure out then its components. This I'm going to call FG perpendicular, and this one I'm going to call FG parallel, perpendicular and parallel to the surface. And this is 25 degrees. So if I want to know what FG perpendicular is, notice that compared to a 25 degrees, this is the adjacent side, and our FG is actually the hypotenuse. It's the maximum one when I put my two components together. So since this is the adjacent side, I can walk myself through that, and I'll just do it once here for completeness. I have here cos 25, which should be adjacent over hypotenuse. My adjacent over hypotenuse. If I then move this FG to the other side by multiplying both sides, I get that FG perpendicular is equal to FG times cos 25. That also means that my FG parallel, this side of the rectangle is the same as this side, so it is opposite. So my FG parallel will be FG sine 25. Now, let's look at what that friction is going to have to be. Now, if it's just sitting there, that means that I have no motion, no acceleration down the ramp, and all the forces are balanced. That means the force of friction is going to actually equal my force G parallel. Now recall, force of friction is going to be mu static, and in this case the reaction force, which is our normal force, which is also going to equal Fg perpendicular. And on this side, Fg parallel, if I put some more values in there, mu s is going to, Fg perpendicular was Fg sine 25, and Fg perpendicular is going to be Fg cos 25. And we can make our life a little easier by canceling out that Fg, and sine over cos is the same as tan 25. By the way, if you get confused by that, just use sine 25 divided by cos 25. Well, if I pick up my calculator, making sure it's in degrees, I'm going to get a value of 4.7 if I round to two significant figures. Again, I could have put and calculated what the weight was. It did give me, in this case, 5 kilograms, but notice that it's really just dependent in this case in terms of what the actual coefficient of friction is and not the actual object. Okay, so let's do one more example with vectors and angles to make it sure you understand. The ramp makes an angle of 24 degrees with the horizontal and has a coefficient of static friction of 0.17. We have a 4.8 kilogram box remaining at rest on the ramp with what additional force must be held in place. So let me go back and let's put in our different forces. Force due to gravity. We also know that we have the normal force. We have friction. Remember, friction should be parallel to the surface. And in this case, we're going to have that force of friction isn't enough. There's going to need to be another amount to make sure we keep it in place. Okay, so force due to gravity, here we are here. We now have 24 degrees here. This is going to be our FG perpendicular, our FG parallel. And in this case, again, remember, we have force FG perpendicular is this one right here. It is beside our degree, so it's adjacent. That means it's going to be our cos. Okay, so now let's look at all the forces that are going to be acting parallel to the surface. Those are the ones we want to be thinking about in terms of what we're going to need to add to make sure our box doesn't move. If we make sure our box doesn't move, we want to make sure all of the forces are balanced. So in this case, we'll have our force, and I'm just going to leave it just as an F, no subscript. That's the one we want to apply. And the force of friction are going to have to equal our FG parallel. That's the force of gravity that's trying to pull it down along the ramp. If I move that around, the force we're looking for is then going to be FG parallel minus the force of friction. Okay, so FG parallel, that is force times of gravity sine 24 minus the force of friction is going to be mu times the force perpendicular. So that'll be FG cos 24. If I put the numbers in, this is what I get. And I'm going to pick up my calculator, and I get 11.84. I'm going to round that to two significant figures because that's the data that I have in my question. So I would have to add an additional 12 newtons of force pushing up the hill to make sure this box did not slide down. Okay, so that's it for the different examples. Please take a read of the success criteria one more time, and hopefully this video will allow you to say yes to all those pieces.